Hi, this video we're talking about mass moment of inertia. Mass moment of inertia essentially is telling us the resistance to rotation. And it has a symbol as I. And when this mass moment of inertia increases, which means it has more resistance, right? More resistance to rotation. More resistance to rotation. Okay. And the definition for I is going to be r squared times mass if this is regarding z-axis. If this is our z-axis, and then you have this mass right here, and the distance from the mass to the z-axis is r, so that would be r squared times r. So knowing that the US system for the mass moment of inertia, that would be distance, that would be meter square, because that's r squared times the mass kilogram. So it's meter square kilogram. That's going to be in SI unit, right? And for US system, then we will have the unit for the distance. That will be, instead of meter, we will use foot square, and the mass unit will be, instead of kilogram, we are using pound mass. So it will be those two units. Okay. Just trying to be clear from beginning, you probably have learned about area moment of inertia before. And in that time, for area moment of inertia, that definition is going to be r squared area. So for example, you have z-axis and you have this object here, and it has area A, not the mass. This is mass. This is our area. And then this area is rotating about this z-axis, and distance is r. So the definition for area moment of inertia is r squared A. Okay. And thinking about this, what's going to be the SI unit? R is a distance, that's going to be meter, and area, it's dimension square. So that will give us meter fourth. For SI unit, for area moment of inertia, is meter to the power fourth, and for US will be the counterpart, that will be foot, right? Foot to the power fourth. Okay, so they both kind of describe the resistance to rotation, and now let's take a look at this. During the reality, what do you want? You want more resistance to rotation, right? For example, for structural engineering, if you want to have a beam, you want to position it, have more bending, more resistance to bending. Okay, it depending on what situation. If you are a figure skater, for example, and you're on the ice here, and you're gonna go do the spinning, triple axel spinning, and you wanted your resistance to be reduced, right? So you will have easy rotation. That situation, your arms and legs are all pretty tucked in, so you have less resistance to rotation. Okay. Now let's look at one more concept. I want to review the Newton's second law. Newton's second law, we learned about F force is equal to ma. That's for translational movement, which means it's moving at xyz coordinate. Translation. And how about for rotation? For rotation, what would be the formula for that? Here for mass, what's its counterpart at rotation? That's when this new concept come along. It's resistance to rotation, because we know mass is a resistance to translational movement, right? For example, if you have a truck versus a toy car, and the truck is going to have more resistance to move because this mass is huge. And however, for rotation, we are not looking at the mass only. We are looking at mass moment of inertia, this I. And this I we're talking about, it is this m mass times r squared. So it's kilogram meter square. So that's going to be meter square kilogram. That's going to be the unit for your mass moment of inertia, I. Okay, and then what would be the counterpart for acceleration then? Acceleration is going to be angular acceleration, right? That's going to be our alpha. Yeah, check out the angular acceleration video from the last time, and then what would be the angular acceleration unit, right? So alpha, quick recap, alpha is the change in angular velocity over time. Angular velocity is what? Radians per second. And then per time. So angular acceleration will be radians per second square. Okay, so that will be the unit for angular acceleration. Now, what will be the driving force to make it rotate? That will be, instead of force, we're going to apply the torque, or we call moment. So that moment we call m. Moment, it's going to have a unit as force times distance. So that would be Newton times meter. So that's our another equation. M equal to I, mass moment of inertia, times alpha, angular acceleration. And we call this M moment, or torque. Okay, now the very last, I want to verify the dimension. I want to make sure the left and right hand have the same equation, have the same dimension for this equation. So let's go ahead and verify it. This moment is equal to I times alpha. And we're talking about this moment is Newton meter. And this I, mass moment of inertia, is going to be meter squared times kilogram. And alpha, being the angular acceleration, it's going to be radians per second square. Let's take a look. Radians basically has no unit, right? Then we span this up. So meter squared is meter times meter. And then we times kilogram, then divided by second square. The reason we arrange this because we start to spot, that meter per second square, that's acceleration, right? And then we also know kilogram, mass times acceleration. So mass times acceleration, that's going to be our Newton. Let's write it down. Newton is mass times acceleration. Newton is kilogram per meter second square. We use this quite often. And so this entire set right here, that's going to be our Newton. And then we have a Newton times meter. That's equal, both hands of equation. So not only we understand this equation I call second law for rotational world. So it's moment equal to mass moment of inertia times angular acceleration. And we also proved that both left and right hand equation has the same dimension. Here we go. So that's mass moment of inertia. We understand its unit. We understand what is for, its resistance to rotation. And depending on your purpose, sometimes you want a resistance to be small, like a figure skater doing triple axel. Sometimes you wanted this resistance to rotation to be high. For example, in the structural engineering field, you don't want to have collapse and you don't have bending or rotation. And we understand how is that related to the rotation, the torque, and angular acceleration. All right, so that's all for mass moment of inertia. I'll see you in the next video. Bye.